announcements. We're talking about the derivative. So let's talk some more about the derivative. I hope you remember. I will refresh your memory about the definition of the derivative. If you have a set L, a language, you can take the derivative with respect to A or B or whatever. And the definition is this is x such that AX is in L. So in words, what you're doing here is you take all strings from L, which start with A, which start with A, and then remove the A from them. That's what the derivative means. I mean, remove the A from the beginning, right? They start with A, you take that one off. Of course, there might be other A's elsewhere inside the strings. All right, and if there are any strings which don't start with A, then you just ignore them entirely. They don't appear in this set at all. Any string from L which doesn't start with A just doesn't appear in the answer at all. And so you can get the empty set, for example, when you take the derivative. All right. So, for example, the if I do something like derivative with respect to A of, I don't know, we did some examples last time. How about all strings which begin with AB, ABX, such that X is in AB star. Another way of saying this is that's the set of all strings which start with A followed by B. If I take the derivative with respect to A of that, what do you get? Yeah?
BX.
Yeah, it's all strings of the format BX. They used to have A at the beginning, but you take that one away. So now it's just all strings of the form BX, where again, X can be anything. Right? But if I take the derivative with respect to B of the same set, DDB of ABX, somebody else want to say what's that going to be? Somebody else want to say? Yeah?
The empty set.
The empty set. Yeah, remember what I said before. If those strings don't actually begin with A, then you just ignore those. And in this case, I'm taking the derivative with respect to B. None of these things start with a B, and so you don't even consider anything in the answer. So you get the empty set as the answer. All right. You can write sort of very, very simple little things like derivative with respect to A of just B. This is the empty set, but the derivative with respect to A of a language which is just A, this would be the empty string, actually the set containing the empty string, right? You start with A and you remove A, and what remains is just a string of no letters. I think these two rules are why it's called the derivative. If you imagine that that's kind of like the number 0 and that's kind of like the number 1, then these look like the rules for the partial derivative in calculus. But we're not going to make much of a big deal out of that at all. All right. I had some more interesting examples of derivatives, and then we will get to talking about what this has to do. Remember, the whole reason we're talking about this is because it has something to do with regular languages and non-regular languages. But let's just look at a few more interesting examples. How about, this is a little strange, derivative with respect to A of X such that X is in AB star. This is just, the set there is just all strings, right? With no restrictions. All strings using A's and B's. Take the derivative with respect to A of that. What is the set which results? Remember, yeah?
Would it be BX?
BX, that would mean all strings which start with B. I think, so you have to imagine I start with any string at all, And if it starts with an A, I take the A away. What remains? I don't think it must start with B then. What remains?
Is it just the same thing?
Yeah, it's just the same set. This is a little weird, but it's true. I suppose by analogy you could call this set e to the x, but you shouldn't, because this derivative is the same thing. Actually, there are many sets where when you take the derivative you get the same thing. There's not just one set, but you get the same thing again. This is weird because when I look at this derivative with respect to a, I feel like this is changing the strings. And so if I take all of these strings and change them all, I shouldn't get the same thing again, but actually you do get the same thing again. It's because what this derivative means, remember, is you consider all the strings in here which actually do begin with an A, and then you remove that A from them, and then you say, what does the rest of the string look like? And the answer is the rest of the string could still look like anything. And that's why the answer is still all strings over here. Very a little strange in my opinion, but strange but true, all right? What about the strings in here which started with a B? They get thrown away entirely. You don't even consider them as part of this answer. But it is a fact you could still get any string possible as the answer of starting with something that started with an A and throwing it away. Strange but true. How about, I guess, some other slightly weird ones. Maybe this is a little simpler. How about x such that, I'm using A, B star as the alphabet every time. Let's say x uses an even number of A's.
Is it d over dx?
Yeah, I didn't mean to write. I meant to say A. Sorry. D dx doesn't make a lot of sense in this context, unless x was a letter, but it's not. I'm thinking of my alphabet here as being A B star. X is in A B star. I'm used to writing D dx because I've been doing calculus all morning. Any thoughts? What do you think?
Would that be x uses an odd amount of A's?
It is, yeah. And this maybe is intuitive. I don't know if this seems obvious. X uses an odd number of A's. If you have something which uses an even number of A's, what's a little weird about this, this on some level maybe seems obvious that if you have an even number of A's and you cancel one of them out, then you're going to have an odd number of A's. But remember, the derivative only cancels an A at the beginning. So what if you have an even number of A's but they're not at the beginning? Then what you're canceling... Anyone have a thought about that? What if there's an even number of A's but they're not at the beginning? Then doesn't that mess this up? Because actually that does not mess it up, because this is a little weird. You got an idea? Yeah?
You only care about the A's?
Yeah, I think in this, when you're doing this derivative, remember, we only consider the strings which actually begin with an A, and then we throw that A away, all right? So when I say, well, what if there is a bunch of A's but they're not at the beginning? Then I don't care about that string anyway, right? The only strings under consideration are ones which begin with an A, and then you throw that A away. So if you have an even number of A's and it begins with an A, you throw that A away. What remains is a string with an odd number of A's. This is deceptively weird in my opinion. Yeah?
It only cares about strings that start with A, and what about strings that start with B, but they still have even number of A's?
Yeah, they would, but they do not appear in the answer.
Oh.
Remember, things which start with B, they sort of become the empty set. So, yeah, they don't exist in the answer anymore. So the only things which exist in the answer are ones where they used to have A at the beginning and then you got rid of it. And now they have an odd number of A's left over. Somewhat strange if you think about it. And of course, I mean, if you believe that, then you probably believe the other way around is also true. So if I take the derivative of x uses an odd number of A's, then the answer is all the things which have an even number of A's. Right? For the same reason. All right, how about, I got another one. This one also looks kind of deceptively obvious, but it is a little strange. How about these are strings which begin with some power of n, some power of a's. So it has a bunch of a's at the beginning. And I take the derivative of that. Any thoughts? I would say there's one kind of naturally obvious answer and one less obvious answer. What do you think?
The a to the n minus 1.
Yes, this is what I think is the most natural answer, and it is correct. This is not a trick question. You started with a string which had a bunch of a's at the beginning, and all you do is you just cancel off one of those a's. So one little technicality is you may look at this and say, what does this mean? Remember, the natural numbers can include 0. What does it mean if the n really was 0? This would say a to the negative 1, but that's not a thing, at least not in this class, right? There is no such thing as a negative power of a value. So I suppose to be very picky about it, we should say n not equal to 0, right? Because in that formula there, n equals 0 doesn't make sense. All right. Anyway, that is what I would consider the natural obvious answer. Here's the less obvious answer, but still correct. A to the nx. Can anyone explain why those are actually the same in this case? They certainly look different because one is n minus 1 and the other is n. Yeah.
Is it because n doesn't have to be the same n?
Yeah, it's because this n, if I ask you, like, what is n here? Well, it can be any number. What is n here? It also can be any number. So there's no difference between these two sets. They look different when you write them in this way. And in a sense, the first one is a more obvious answer to the question of what the derivative is. But actually, these are the same set again. So these, I will just emphasize, they are the same set. One of the morals of the story here is sometimes two sets which can look different, just the way you write them might look different, but they may actually be the same set. All right? Okay, great. How about, I got plenty more. How about derivative with respect to a of a to the n, b to the n? This one, again, for the same reason, it's very similar. This time, when you cancel off one a at the beginning, that's what the derivative means. This becomes a to the n minus 1 b to the n. And I suppose you should say n can be 0 here. Usually I'm not going to mention that, but it's true. N is not allowed to be 0 anymore because that wouldn't make sense in the exponent there. What's interesting to think about, is that the same? Like I have this n minus 1. Is this the same as this, a to the n, b to the n? Or are they actually different in this case? I think they're actually, what's the difference?
It's because for like the first one, you could change the number for A, and that would be fine. But if you did it for this one, it also changes for B, which.
Yeah, right. These n's are the same. So the second set here are things where the power on A is equal to the power on B. This set is when the power on A is 1 less than the power on B. So they are not the same set. Like for instance, A squared, B squared is in this one, but not this one. A to the 1, B to the 2 is in this one. So these ones are not the same. They look different, and they really are different. All right? Okay, I got two more somewhat weird examples, and then we'll talk about what this has to do with regular languages. X and AB stars such that X starts and ends with the same letter. Is inspired by, this appeared on the test. I asked you to give me a regular expression for that. X starts and ends with the same letter. I'm doing the derivative with respect to A. Any ideas? Yeah?
Is it XA?
XA, he says. Yeah, I think so. So he said XA. Yeah, why is that?
Because it has to start and end with A, and then you get rid of the A, so then you can have a bunch of A's or B's, but you just need an A at the end.
Yeah, right. So this, remember, when I'm taking the derivative with respect to a, I consider only the strings in here which actually do start with a. But since I said starts and ends with the same letter, that means they also end with a. And then I remove the a at the beginning. And so it looks like any string which ends with a. Sometimes you got to think it through a little bit. And it's not always immediately obvious what the answer is supposed to be. Yeah?
For not this one, but the one we previously did, if we made that to the derivative with respect of a to the n, does that do anything?
This is a good question, and actually this is very much relevant to some examples that we're going to do next. So yeah, can we say that same one? What if I did d, so it was this, a to the n, b to the n. The problem with, so the question was, what if I did derivative with respect to a to the n? Right here I put an n rather than just a. Precisely that is not really allowed, because what you put down here has to be either an individual letter, like an A or a B, or it can be a string, A, B, A, or something like that. A to the n is not really a string, though, if n is a variable, right? Like I would say this, you're not being specific enough about what the n is here. Now you could just say, like, don't call it n, maybe it's a little clearer if I maybe call this I, then this would be a to the n minus I, b to the n. And that, where I is some specific number, not a new variable which could be anything. This n can be anything, but this, what goes out here has to be specific. But yeah, you would get something like that. Great. Okay, I think we're on board with the derivatives. I hope so. I'll try to remind us what's the purpose of the derivative, all of this business. I remember I had this example that I wrote down last time. And I will just, this is a DFA. I'm going to give names to the states this time. The details here are not so important, but I'll call that X, Y here. Sorry to draw this complicated thing again. All right, this is a DFA, and let's call that M, right? As is, it has a certain language, the language of M, right? But what I was talking about yesterday and what got us talking about the derivative is what happens if you move the starting state. For example, if I move the starting state from S to T, the effect is whatever strings used to be in that language, they started with A, but then I'm going to take that A off of them. And so moving the starting state to T changes the language to, now it becomes the derivative with respect to A of whatever the original language was. If you change the starting state to T, it changes the language to that. That's because whatever used to be accepted went through this edge first, and now if you move the starting state, you just don't have to do that first A anymore. And so all the strings which will be accepted, they're the same strings, only they no longer had that A at the beginning. All right. What about if I move the starting state to X? It has to do with moving it like through these arrows which have certain labels on them. If I move the starting state to X, moving it to X makes the language derivative with respect to B of the language of M. And in fact, in this example, that set is the empty set. If you start, you can tell by looking at the diagram, if you have X as the starting state, then there are no strings which can be accepted from there. All right, what if I move the starting state to R? Anybody, can I express that in terms of derivatives? Anyone want to guess?
Is it d over d b squared?
B squared?
Or is it just b? Or a.
I think you mean AB, yeah, right. In order to get from here to there, from S to R, you go through A and then B. So that is what will happen. Sorry to scroll the picture. Moving the starting state to R makes it derivative with respect to AB, like that. All right? Great. Now, in this particular example, here's something interesting. Moving it to R makes it into this derivative. That's why AB? It's because the way to get to R from S is to go A and then B, right? That's why it was AB. But consider this. I could also go to R in a somewhat stupider way by doing A, B, 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 B. AB to the fourth also lands me at R, all right? What that means is moving the starting state to R makes it this, and also this, D, D, A, B to the 4. And what that means is those two sets must be the same set, just because the language becomes, if you move the starting state to R, the language becomes something. What does it become? Well, for one reason it becomes this, but for another reason it becomes this. And those answers have to be the same answer. And so in this example, so in this case, this derivative with respect to AB of this language is also equal to this derivative with respect to AB to the 4 of the same language. And you could do this, I mean, it's not only AB to the 4, but it's also, you could go around that loop in the diagram again and say this is also the same as, I think it would be AB to the 7 if you went around it twice. Yeah.
For the X1, why can't you do DAA too? So you can get to X from there, right?
Yes, it's true. And what that means is that, so I'll write that down. What that means is, so similarly, it means the derivative with respect to B of this language also equals the derivative with respect to AA of the same language. Because in the diagram, when you go B, it's the same as doing AA from the starting state. All right. So actually, what I'm trying to get at here is many different derivatives end up giving the same answer. Right? And in fact, you can tell by looking at the diagram which of the derivatives will end up giving you the same answer, because it's just the ones where they go to the same place if you follow the arrows. Yeah?
Does that mean the number of states correlates to the number of derivatives?
Mm-hmm. This is exactly what I was about to say. It means, since this is a DFA, the F, remember, means there are only finitely many states. In this example, there are 5 states, which means no matter what derivative you're doing, there are only 5 different answers you could possibly get. And in fact, there could be fewer than 5 if some of them coincidentally end up being the same. But this DFA, well, really, I mean, you could say this about the DFA, but really it's a statement about the language. This language can only have 5 possible derivatives. Because there's only 5 states in the diagram. All right. What does this mean generally about any DFA? Any DFA has finitely many states, and for all of these same reasons, it means it can only have finitely many derivatives. Like if there's 10 states, there could at most be 10 different answers you could get when taking the derivatives. Even though there are infinitely many ways you could take the derivative, you're only going to get finitely many different answers from something that comes from a DFA. Any DFA gives a language with only finitely many derivatives. This is kind of the deep fact. And I'm going to write this as a theorem. just saying this, I can say all of this without mentioning DFAs, just in terms of languages. I'm talking about the language of a DFA, which is a regular language. So I'm going to say if L is a regular language, then L has only finitely many derivatives. This is the big important relationship between regular languages and derivatives. Only finitely many derivatives. What I mean is, even though there are infinitely many different ways you could do the derivative, you could do, derivative with respect to A or B or AB or BA or BB. There's infinitely many ways you could do the derivative, but the possible answers you can get, there's only finitely many different possible answers. All right. Now, this theorem as written is interesting. It is super useful when it comes to detecting non-regular languages. And I'm going to write when it comes to non-regular languages, it's better to write this in terms of the contrapositive. Anyone remember this word? What's the contrapositive of that theorem? Any discrete math wizards out there? Remember? Yeah?
Is it if L has only finitely many derivatives, L is regular language?
That is the converse of this, which the converse, remember, is not equivalent to the original statement. The contrapositive is another way of saying it, which is automatically true if the original thing's true.
If L has infinitely many derivatives, then L is a non-regular language.
Yes, if L has infinitely many different derivatives, then L is non-regular. And this is the way we are always going to show something is not a regular language, by showing it has infinitely many derivatives. And I don't know if that seems complicated, but it's usually fairly easy to do. Infinitely many different derivatives. Then L is non-regular. Let's just try it out. This is pretty easy to check. So everybody's favorite example of a non-regular language. So let's show that A to the n, B to the n is non-regular. If you look back in your notes like a couple months, you will see we actually did a proof of this, although it was fairly complicated and very much specific argument specifically for this language. The derivatives approach is much easier and also much more general purpose. You can use the derivatives in pretty much any example. The derivatives will work to do the demonstration. Anyway, let's show that this is non-regular. So we need, in order to show that it's non-regular, we need to show it has infinitely many different derivatives. Right? Now, we have to just think about, are there different ways to take the derivative? Are there actually infinitely many different ways to take the derivative to get a different answer every time? Of course, I could do derivative with respect to A. Can I call that L? Would you mind? This is A to the n minus 1 B to the n, right? Can anyone give me a different derivative that's different? I said different twice. Yeah?
A to the n, B to the n?
You can't use n when I want to say derivative with respect to something else down here. It has to be a specific string that you say. How about a squared? Can anyone say what's the language going to be there? That means you just cancel the first two a's. What do you think?
A to the n minus 2.
Yeah, this is a to the n minus 2, b to the n. And are those sets really different? I mean, they look different, but sometimes they might look different, but they're actually the same. These ones really are different. Actually, we already kind of talked about this. Yeah, the first one here is one in which the number of a's is 1 less. This is when the number of a's is 2 less than the number of b's. So those really are different sets. Anybody see where I'm going with this? Can we what's the next set that I'm gonna write here? The next.
Just the derivative of a cubed.
Yeah, we can do this again with a cubed, right? So this is a to the n minus 3 b to the n. And again, this is different. That's a different answer. This is a set in which the number of a's is 3 less than the number of b's, and that's different from these other two sets. All right? Do you believe me that you could just continue this and say that you get infinitely many different possible answers here? All right. Now, this is the basic idea. Usually how I would write this, just because we're going to be doing so many different examples here, consider that sort of a sidebar scratch work. Here's the way that I would typically write this thing. I would say let di be derivative with respect to a to the I of L. So what I'm trying to say here is I'm just describing all the different derivatives that you could take here. I mean, this is actually not all possible derivatives, but these are the ones that I want to focus on. I'm taking the derivative with respect to a to the I of L. And then what is that? Sorry, I don't have a lot of horizontal space here, but this is equal to a to the n minus I times b to the n. All right. And those sets are all different. These sets are all different. There's infinitely many of them, of course, because I could be anything. And so L is non-regular. The end. All right. So in a problem like this, you're going to have some of these to do on homework and so on. Your job basically is just to decide what's the strategy for taking various derivatives over and over again. And in this example, it's not so hard to see that you should be taking the derivative of a over and over again. And that's what these are. I'm taking the derivative of a every time. And the result is it changes the set every time. You're not going to get the same thing again after taking those derivatives. All right? This is how we do it. Let's just try a few more examples. You will see actually in other examples, the proof goes very similarly. So you actually don't have to, this is like a little proof that I wrote, and you do have to write similar things in other examples, but actually the structure of what you're writing is very similar from one example to the next. So if you can remember the basic format, it's not a problem. So let's try to show, how about this? A to the n, b to the n, c to the n. We haven't had c's in a while. Let's show that this is non-regular. You just have to, I'll write this like a little proof. There's not a lot to it, but it is a little proof. Again, you just have to think about what's my strategy for taking the derivative over and over again. Typically, you want to do something which will cancel out the first letters, because that's what the derivative does. And in this case, the a to the n is on the front, so I think I can just do exactly the same thing. Now, not every detail of what I'm about to write is exactly the same, but I'll start off the same at least. I'm going to call each of these different derivatives. I'm doing derivative with respect to a to the I. Let that be, I'll call them di. And then what is that as a set? Here is slightly different, although not a whole lot. What do you think? Ignoring someone who has had their hand up a lot. What do you think?
A to the n minus I, b to the n, c to the n.
Yeah, right. A to the n minus I, b to the n, c to the n. This derivative with respect to a doesn't affect the b's and the c's. It only cancels a's at the beginning, right? Anyway, are those sets all different? I think they are. The number of a's has fewer than the numbers of b's and c's, and how much fewer is different for each of those different sets. So I can just say these are all different. So L is non-regular. That's all there is to it, really. Let's try another one, slightly different. How about L is BA to the N, AB to the N. Babinabbin. We want to do something similar. Really, the only thing that you need to think through is just what should I be taking the derivative with? Now, in this case, you should not use a to the n, because these strings don't begin with a anyway, and so if you just cancel a's at the beginning, you're going to get the empty set or something like that. So don't say a to the n. Fill in the blanks here. Want to do something similar to previous examples. Yeah?
AB to the I, or BA, sorry.
Yeah, I think BA to the I will do it. Sorry, I have a bad spot on my screen when I write on it. So I have to over scroll here, like so. BA to the I. Yeah, the idea, generally speaking, if I can make sort of an editorial comment, I would say you try to cancel the front of the string. And in the previous example, the string began with a to the n. So you think of this as starting off with a lot of a's, and I just cancel some of them. You cancel one of them, or two of them, or three of them, etc. In this example, the string is beginning with a lot of BAs, and so I just cancel a bunch of those. BA to the power I. All right. And then what do the strings look like after doing that? You know, it looks like this. If this looks familiar, these examples tend to go in the same way. BA to the n minus I, because I canceled off a bunch of them at the beginning there, followed by AB to the n. And then, as usual, we say these are all different. You should make sure that's really true when you say this, but it's because they have different values of I here, and when you change this I, you get different sets there, all right? These are all different, so L is non-regular. I hope you are beginning to agree that, like, yes, you do have to write a little proof, but it's usually like 2 sentences, and those 2 sentences are always the same. Really, the whole deal is deciding what that should be, and then correctly saying what the resulting set is. All right. This is so formulaic. You may worry that, like, doesn't this always work? Even if it is a regular language, you should worry, like, this seems like such an easy way to prove things. Is this like too easy? What happens if you try to do that? What if it really is regular? That's what I'm trying to ask. What if it really is regular, but we try the same thing? For example, this language, A to the N, this actually is a regular language. Why is that regular? It's because, you know, here's a DFA for it. This is a DFA which accepts the language A to the N, right? So it is a regular language. What makes A to the N, B to the N not regular is because you have 2 different things with matching exponents, and that you can't do with a DFA. But having only one thing with matching, it doesn't have to match anything else. It's just one thing with an exponent. That's totally easy to do on a DFA. So let's say this is L. What if, but you could imagine doing the same proof. So I want to know, what would happen if you tried to write the same proof? Well, I would say something like, let di be the derivative with respect to a to the I, right? Because I have a's at the beginning, so I'm going to cancel off some of those a's. What does the answer look like? It looks like a to the n minus I. And these are all different. So L is not regular. There must be a problem with that. Can anyone say? Something that I wrote there is not right because L really is regular. So this argument cannot be sound, even though it looks exactly the same as all the other ones we've been writing. Any ideas? I suppose I only really said two things here, right? I said that is the answer you get, and then I also said they are all different. One of those two things must not be correct. Is this really the answer you get when you take this derivative? I have a bunch of a's, and I cancel off I of them. I think that really is the resulting set. What about this? These are all different? Are those sets actually all different?
Couldn't they all just be a to the n?
Yeah, this is similar to one of these weird examples that I was talking about at the beginning. They look different, but actually these sets are all the same because n can be anything in this formula. So all this says is a to some exponent which can be anything. Because n can be anything, that means n minus I could be anything. Actually, all of these sets, so the error here is that statement. They are all different. Actually, in this example, they are not all different. These sets are actually all the same, even though when you write the formula as a set, it doesn't look like it, but they're all the same because all it says is you have some number of a's. You might say, oh, well, I have some number of a's, but then I take some of them away. I say, yes, you still just have some number of a's. All right, these are all the same. In fact, they're all the same as a to the n. Those sets are all the same. They are not all different. And so you cannot conclude that L is non-regular. And in fact, L is regular. Right? So this is what can happen if you try to do this on a regular language. All right. Excellent. Let's do a couple of more interesting ones. And I got some for you all to try. And that will do it for us. So how about harder ones? Give me a hard one. This is a saying that we have in my family among my kids. Because one time we went to like a burrito place. It wasn't Chipotle, it was someplace like that. And my kid just walked up to the counter and she said, give me a hard one. She meant like a hard shell taco. We thought it was funny. Slightly harder ones. These are not all really hard, but how about this? L equals a to the m, b to the n, a to the n. This one is a little harder, just because for this one, what you would naturally try to do doesn't work. And let me just, I will write this in green, because this is not going to work. But this is what I would try. I would say, okay, let di be the derivative with respect to a to the I, because I want to cancel off the beginning of the string like I always do. And then this, when you take this derivative, what you get is a to the m minus I, b to the n, a to the n, right? And then I say, sorry, can you even see that? Well enough. And then I say those are all different, and so this is not a regular language. Anyone see the issue with that? It has to do with the fact that this m is different from these n's, all right? Actually, when I do this, these sets, they are all the same. For the same reason that I said like up here, right? These guys, they're all the same because this just says some number of a's. And it does, since this doesn't have to match anything else. What does this say? This says some number of a's followed by b to the n, a to the n, equal numbers of b's and a's, right? But this number of a's has nothing to do with those numbers of a's. And so there is no special condition on how many a's are in here. So I will say these are actually all the same. It just says some number of a's followed by matching numbers of b's and a's. And so this is sort of a failure because you need to choose your derivatives so that the answers all turn out to be different. And that was a bad choice. They don't all turn out to be different. Really what's necessary is to play around with this thing, right? The thing that makes this non-regular is we need to sort of exploit this part, right? What makes it non-regular is the fact that you have this exponent which has to match that exponent. And if you take the derivatives to cancel parts of the first one, they will no longer match the second one. That's the way that we've done these examples. The previous examples all worked out in that way. The problem is this part is kind of shielded by that thing. How do you take your derivatives to get to that? I want to cancel parts of the b, right? But they're blocked by this other thing. Anyone have a cute idea? There's a cute idea to get around this issue. Yeah?
Would you take the derivative of a b to the I with the a not, like the exponent, just the b part has the exponent?
Right. And a is just by itself?
Yeah.
This is a good idea. And actually this will work, although it's I have a slightly cuter version of this idea. But he says, take the derivative using a b to the I. That is a single a followed by some number of b's. Is a single a enough to break you through this thing? This is what you should be worried about. This thing could perhaps consist of many a's. Do you have a thought about that?
Could you do a to the m?
Okay, this is a good revision of the idea, but the problem with that is m is not a specific number, it's a variable.
Could you do like a to the I, b to the j?
This may work, although that now you have two variables in there. It's like double infinite different.
Could you just do a to the I, b to the I?
A to the I, b to the I. This is a pretty good idea. So some of these ideas which I am reluctant to accept are technically correct, although a little confusing. And you have another idea?
Could you just do b to the I?
He says just b to the I, and this I agree with. This is not obvious at all that this will work, but this is the way to do it. Just b to the I. Can you explain why that actually works?
Because the beginning number of a's can also just be 0 a's and then just be the b to the n a's.
That's right. When I take the derivative with respect to b to the I, these strings, most of them start with a's, and so this doesn't do anything to them. Remember, technically what that means is they do not appear in the answer at all. So what this says is I only consider the strings which begin with b to the I. Now there are some of those because some of these have no a's at the beginning at all, right? This m can be 0, like he said. And so some of these, let me just give some commentary here. Some strings in L do not begin with a, right? They really don't. I kept on saying like this a to the m is like a shield in front of these other ones. But actually m can be 0, so not all of them are shielded in this way. Only some of them are. And so when I do the derivative, just without the a at all, I'm only considering the strings which don't start with a's. They only begin with b's, all right? So in this derivative, we only consider the ones which start with b. With b to the I, in fact. So what that means is, i.e., m was 0, right? M is the exponent on that a at the beginning. And so, this is a deceptively good idea. It looks like a bad idea at first, but actually this is the deep, proper way to do this. And so, can we say what actually is the derivative? What is the set that you get when you do this? Yeah?
b to the n minus I and then a to the n.
B to the n minus I, a to the n. Yeah. What happened to the shield at the beginning? I'm only considering the strings which didn't have any of those a's at the beginning to begin with. And so, after canceling the first I, b's, this is what remains. And those are all different. So, it's not regular. These, I wrote, are all different. So L is not regular. Right? So sometimes you got to be a little cute about choosing exactly which derivative you're doing, and it's not always obvious. That's the moral of the story. Any thoughts or questions about that? All right, I got a few more, and then I got some for you to try. How about derivative? No, I tell you the language. Show me that this is not regular. X in A, B star such that X has the same number of A's and B's. This one's even weirder because I didn't tell you anything about the format. Like this is not like A to the N, B to the N, whatever. I don't tell you what they start with, what they end with, or anything. Generally speaking, you want to try to cancel the beginning of the string, but you don't even have any idea of what the beginning of the string looks like in this example. I just said it has the same number of A's and B's. But you can do a similar kind of stupid-looking approach, which actually works great. I will say let di be, let's just do this, derivative with respect to A to the I. So even though these strings do not all begin with A to the I, some of them do. And I am only considering those ones which do when I take this derivative. Can anyone say, perhaps in words, what these strings look like? So you have to imagine these are the strings which originally they had the same number of A's and B's, and I am assuming that they started with A to the I, and then I get rid of the A to the I at the beginning. What can be said about what they look like now? Right? I less A's than B's. Yeah, this is a little hard to write in words, but I will say X has I fewer. Actually, it's fewer, not less. I'm not much of a grammar police here. X has I fewer A's than B's. Right? Even though we don't know what the strings start with, we can just sort of like pretend that they start with a block of A's and cancel those A's off. And now X has I fewer A's than there are B's. And those sets are all different, right? If you use I equals 0, then they have the same number. If you use I equals 1, there's one less A than there are B's. These are all different kinds of sets. So these are all different. Great. So L is non-regular. All right. All right, one more. And then I have some for you to try. And I think that'll do it for us. Thank you for your patience and participation on the last day before break. How about L is, this one's cute, X squared. Such that X is an AB star. X squared. That means the string itself is a square. So this is strings like, you know, A, B, A, B, A. This is a square because it is equal to something repeated twice, right? Or B, A, B, A. That's a square also because it is something repeated twice. All right. Now this one also, you don't have much of a handle on what the structure of X is, right? I didn't say anything about what happens at the beginning or something like that. So there's no obvious thing to just take the derivative of what you see at the beginning. you're in such a situation, usually what works is just to do something like derivative with respect to a to the I. I choose A. I mean, you could choose B. It doesn't matter. But and then you have to think a little hard about, you know, what are you actually going to end up with in this case. So maybe I'll leave that as a blank to fill in. But what this means here is we are assuming that this thing, which looks like x squared, can I write it as xx? Assuming that this starts with a to the I, then we cancel the a to the I, right? Then remove it. What's it going to look like after that happens? Well, this assumption you can use here. What that means is, so x, well, not just that, but assuming that this starts with a to the I, what that means is that x looks like a to the I followed by something else. And so x squared looks like a to the I, y, a to the I, y. All right, we're only considering those strings which do begin with a to the I. Now, since those things are squares of something, their full format looks like this. And now actually we do know what the format looks like. So can you say what does it look like after you take the derivative? You cancel these a to the I at the beginning, and what remains is that. So what this set is, this is not at all obvious by just looking at it, but it's that. It's a string which looks like something, followed by a bunch of a's, followed by, again, the same thing that you saw at the beginning. All right. And are those sets different for various i's? Yes, they are. Like I equals 1 means there's one a in the middle. I equals 2 means there's two a's in the middle, and so on. Those are all different sets from one another. So these are all different. So L is non-regular, right? That's how we do it. Any thoughts about that one? That one is a little weird. All right, I got some for you all to try in our remaining 15 minutes. How about, so in each one, show that this is non-regular. So that last one there is for binary strings, where the bar, I'm using the bar to mean not, so if you think of this as a bits of 0, 1, like the bar changes a 0 to a 1 and changes a 1 to a 0. That's what I mean by the bar. I would say the first one is easy, the second one is a little stranger, and the third one is the strangest of all. Feel free to chat with your friends if you've got them. Nobody says irregular. I don't know why, but that's not the way to be. Second one's a little harder.
So you subtract I and the exponent. So b to the n minus I.
No, could you?
So far as the sun, you're only,
You do the first one.
Actually, I think
If
what
you're
you're
starting
gonna
with,
write here
if you're doing B, then you'll.
Otherwise, you have the first one.
Okay, it really has to be
Yeah,
eight.
they're all different because it's.
Anywhere in the second one? Can I give some advice on the second one? I see a lot of people breeze through the first one and then immediately halted on the second one. First of all, the derivative that you're using, it better be a to the I, because these strings begin with a's. There's no funny business about that. So your derivative should be with respect to a to the I. The question is then, what does the set look like after doing that derivative? And how exactly can you explain that their sets are all different? Yeah, that was good. Now what? That's the question.
But you get the same, right?
Yeah, this is the derivative.
Okay.
And now are all those sets different?
Thanks.
They are actually. I mean, if they weren't, then it would be. I would have told you to do it that way. So you really have to write this part also. Just, if you just write that, then they're not all different because it's just some number of a's and some number of b's.
But like, you're subtracting I, right? So
Yeah.
wouldn't n automatically always be less than m if in the start it was less than m?
Yeah, so when you start, n has to be smaller.
Yeah.
After doing one of these derivatives, actually it has to be even smaller, right?
Right, yeah.
So, and that sounds like it's saying the same thing, but it's not quite the same because, for example, n less than m means that n could be only one less than m. But actually after the first derivative, it has to be at least two less, and that's different.
Okay.
And after the next derivative, it has to be at least three less, and that again is different.
You get the third question right now.
And it's a little tricky.
What's the third question?
Oh, sorry, I scrolled it away. Can we just talk about these? Sorry, because we got to go in 10 minutes anyway. The first one, everybody did great. You do the derivative with respect to b's, and you get a set like, so in this case, your derivatives all look like b to the n minus I, a, b to the n. And those are all different because this n has to match that n. And so in the case when like I is 1, it means this one is 1 less than that one. When I is 2, it means this is 2 less, and that's different. So those are all different. This one, what I said is this is the derivative you want to take, and that's what the set will look like when you take this derivative. The hard part here is just convincing yourself that these sets are all different, but they really are different. What this means is that the power, so in the original set, the power on A is less than the power on B. In this set, actually the power on A, the n is already less than m, but the power on A now is even less than that. It's like 1 less, or 2 less, or 3 less. So how I would describe this set is that the power on A is I, let me say this better, at least I less than the power on B, right? And so, for instance, the first one would say, the first of these derivatives would say the power on A is 1 less than the power on B. The next one would be the power on A is at least 2 less than the power on B. And the next one would be 3 less, and those are all different sets. This is a little confusing in my opinion, but it's that's the way it goes. These are all different. All right, any thoughts about that? It's a little tricky. A little tricky one. How about the last one? I didn't see anyone who really did the last one because you were thinking about the previous one. X followed by x bar. Actually, this is kind of like the x squared one. So the thing is, you don't actually know anything about the structure of x, so you might as well just do, let's say, this is not a's and b's in this one, it's zeros and ones, but let's do 0 to the I. Tell all your friends we did 0 to the I. They will say, isn't 0 to the I equals 0? And you say, well, yeah, kind of, but not this time. So if you do this, that means when considering this derivative, I am assuming that these strings already begin with 0 to the I, right? So when I do this, we're assuming, when I do that, this assumes the string starts with 0 to the I, all right? And that means this string x bar actually must look like 0 to the I followed by y, something like that. I'm doing a similar trick that I did last time. And then 0 to the I y bar, like that. And then if you like, actually, you can remember the meaning of the bar. The bar just changes a 0 to a 1 and changes a 1 to a 0. So you can kind of simplify this over here. What is that? You can sort of do the bar. The bar changes every 0 to a 1.
Becomes or 1 to the I, y.
Yeah, it becomes 1 to the I, y bar. I'm sure that's exactly what he said. When you do the bar of 0 to the I, it becomes 1 to the I, and then whatever the bar of y is, it's the bar of y. All right. So this is the format of the strings, and then when we do this derivative, we cancel the initial 0 to the I. So that means these sets, derivative of L looks like y, 1 to the I, y bar. And those sets are all different for different values of I, because the I just tells you how many ones are in the middle, and they'll be different. All right, and I think that will do it for us. Hope you all have a good break. We will have homework due on the Tuesday, when we come back, so not during break, about derivatives.